Welcome to today's deep dive. We're doing something a little different today. We're tearing away the comfortable, polished illusions of software.
Completely tearing them down.
Yeah, we are looking at a stack of raw, highly technical developer notes regarding the actual architecture of a massive, high-performance physics engine. And if you are joining us, you're the kind of person who doesn't just want to see the simulation run.
Right.
You want to know the physical, mathematical reality of how that illusion is sustained right down at the atomic level. And really what happens when the underlying math goes horribly catastrophically wrong.
Which it does. I mean, the documents we're analyzing today are fundamentally about survival. And I don't just mean the survival of the characters within the digital world, but the literal survival of the computational system itself.
Yeah.
We're exploring that exact intersection where the beautiful abstract logic of modern software collides really violently with the unforgiving physical limitations of silicon hardware.
To really ground this entire discussion, we need to establish the specific parameters of the simulation that this engine is running. So I want you to conceptualize a photorealistic, post-apocalyptic, ruined city.
A really bleak environment.
Incredibly bleak. It is entirely buried in this relentless, howling snowstorm. And the simulation is actively tracking highly trained tactical agents as they navigate these desolate, frozen streets.
They're moving dynamically, snapping into cover behind abandoned, snow-covered cars.
Exactly. And the visual and physical fidelity is absolutely staggering. When a firefight breaks out, the engine isn't just playing some canned animation. It is physically calculating the real-time trajectories of hundreds of individual bullets.
And not just the bullets. It's tracking thousands of microscopic concrete debris particles flying through the air as those bullets shatter barricades.
Yeah, snowflakes dynamically accumulating on the agent's shoulder gear based on atmospheric wind vectors. It's insane.
And simultaneously, right, beneath all that physics and rendering, there are these incredibly complex automated inventory systems running in the background.
Oh, right, the loot systems.
Exactly. These systems are constantly sorting freshly scavenged tactical gear, calculating armor ratings, categorizing contaminated salvage pulled from the ruins. Every single element, from the trajectory of a bullet to the stat value of a scavenged rifle, relies on this uninterrupted stream of mathematical perfection.
It's a digital symphony. It's processing billions of calculations per second just to maintain a flawless 60 frames per second. But our source material today focuses on an apocalyptic failure state.
Worst case scenario.
Right. Imagine all of this running perfectly and then instantly the entire simulation completely freezes. There's no minor visual artifact. There's no temporary drop in the frame rate where the snow stutters.
No warning at all.
None. It is an instantaneous, catastrophic, total Sitem crash. The architecture violently terminates itself. The photorealistic snowy apocalypse just vanishes, dumping the user back to a cold desktop screen.
And what's wild is the developer notes reveal the culprit isn't a memory leak. It's not a thermal overload on the GPU trying to render too many volumetric snowflakes. The failure is microscopic.
Microscopic.
It stems from a mathematical paradox buried deep within the standard rules of modern CPU architecture. To understand how developers prevent this digital apocalypse and keep the ruined city functioning, we have to descend far below the high-level game code. We have to look at the raw metal of the processor.
Okay, let's unpack this. We really have to start at the foundational building blocks of this simulated reality. When the physics engine calculates something requiring extreme precision, say, the exact fractional spatial coordinate of a bullet striking the steel door of an abandoned car, it relies on the IEEE 754 standard for an F32 floating point number.
Right, the F32, which basically means we are talking about 32 microscopic physical containers, transistors, just lined up in the silicon.
The architecture of that F32 container dictates literally everything about how the simulation handles reality. The standard physically partitions those gov2 bits into 3 distinct segments.
You've got the sign bit at the very front, just a single physical switch dictating positive or negative.
Simple enough.
Right. Following that, you have an 8-bit exponent. The exponent basically acts as the simulation scale multiplier.
So if the engine is tracking the macro distance between 2 city blocks, the exponent scales the number up.
Exactly. But if it's tracking the microscopic width of a single flying shard of concrete, the exponent scales the value all the way down to the atomic level.
Which leaves exactly 23 physical switches remaining for the 3rd segment, the Mantissa. And the Mantissa is the detail.
It's the highly specific fractional data holding the exact spatial coordinate of that concrete shard.
Right, so if we have a coordinate value of, say, 10,000.12345. The 10,000 is handled by the exponent scale.
While the Mantissa fights to hold on to that tiny 0.12345 detail at the very end of the physical hardware register.
And that physical constraint of having only 23 bits for the Mantissa is where the architectural cracks begin to form, right?
Oh, absolutely. The hardware reads all 32 electrical charges simultaneously. It slams them through logic gates in the arithmetic logic unit to perform calculations. The fundamental reality of computing is that you simply cannot fit an infinite amount of mathematical detail into a finite physical container.
Which sets up the engine for a phenomenon the developers call catastrophic cancellation. Let's look at this through the lens of our tactical simulation.
Okay.
An agent is in a heavy firefight. They're taking cover behind that abandoned car. The engine has to determine if an incoming bullet strikes the steel door or grazes past it by a millimeter.
To calculate that impact angle, the engine has to physically subtract the bullet's spatial coordinate from the car door's spatial coordinate.
But before the hardware can actually perform a subtraction, it has to structurally align the decimal points of the two numbers.
This is the critical flaw. If the car door coordinate is a massive integer value representing its place in the massive city grid, but it has these tiny fractional details representing its exact angle in the snowbank, the silicon must literally shift the bits of the smaller details down the row of the physical register to align the exponents.
And as the hardware shifts those electrical charges to the right to align the decimal points, the tiniest fractional details, the exact microscopic angle of the bullet, hit the physical wall of the 23-bit Mantissa container.
They get pushed completely off the edge of the register.
They just vanish into the silicon. They are permanently deleted from existence before the subtraction even executes.
The architectural implication of that physical limitation is massive. Because think about it, the large whole numbers representing the macro coordinates perfectly cancel each other out during the subtraction.
Right, because they're basically occupying the same space.
Exactly. The engine then expects to find the tiny remaining decimal details to resolve the microphysics of the impact. But because those details were pushed off the edge of the Mantissa and deleted, the hardware is left reading absolute garbage noise in the lowest registers.
The macro numbers canceled out, and the micro details were already destroyed by the structural alignment. That is catastrophic cancellation.
The bullet's trajectory loses its microscopic precision entirely. The collision detection fundamentally fails.
And the physics matrix might suddenly calculate that the bullet phased straight through the solid steel of the car door, striking our agent and completely shattering the physical laws of the simulation.
Now, standard software logic might suggest simply expanding the container, moving from an F32 to an F64 double precision float to give the Mantissa 52 bits instead of 23.
But in a massive physics engine calculating millions of dynamic particle collisions every single second, doubling the memory bandwidth and processing time for every single coordinate would cripple the frame rate.
The simulation would crawl to an absolute halt. The developers cannot sacrifice performance like that, so they have to engineer a hardware exploit.
And this is where the developer scripts get crazy. Specifically, a crucial file noted as fp.rs. It details how they bypass the standard limitations of the CPU using FMA or fused multiply add.
Normally, standard software multiplication forces the hardware to round off data, chopping off those trailing details to fit the 23-bit container, and then subsequent subtraction forces a second rounding phase. It's a compounding loss of precision.
But FMA fundamentally changes the physical routing inside the CPU.
It utilizes a wider specialized internal path built deep within the silicon of modern processors. It routes the data into what computer architects call an internal pipeline latch.
We can visualize this latch as a massive temporary holding area that completely ignores the 23-bit Mantissa limit.
Yes. When the engine forces the calculation through the FMA pipeline, the hardware executes the multiplication and the addition in a single, continuous, indivisible physical motion. It uses an intermediate register that is essentially double the width.
The developers use a highly specific mathematical trick to exploit this wide internal path, written as -c times d plus cd.
Right, so if CD represents our flawed rounded coordinate, where the tiny fractional details were chopped off during a standard calculation, the engine purposely takes the original raw coordinates, C and D, and forces them into the FMA pipeline.
Explicitly making one of them negative.
Exactly.
Yeah.
Inside that massive internal pipeline latch, the hardware calculates -c times d with absolute unrounded precision. Because the pipeline is physically wide enough to hold the entire mathematical result, not a single microscopic detail is pushed off the edge.
You have a perfect, massive negative coordinate sitting in the internal latch.
Then, without ever leaving that internal wide path, the hardware adds the flawed, chopped CD coordinate. The massive whole numbers of the perfect negative calculation and the flawed positive calculation are perfect opposites.
They violently cancel each other out to absolute zero inside the pipeline.
And the only thing left behind in the internal latch is the exact silicon noise. The tiny microscopic fractions of spatial detail that were originally pushed off the edge and deleted in the flawed calculation.
By weaponizing negative math inside a fused pipeline, the developers perfectly extract the lost precision of the physical world.
The engine retrieves that perfectly rescued microscopic bullet angle, injects it back into the final collision calculation, and the physics are saved.
The bullet strikes the steel door, the concrete sparks fly, and the agent survives. The illusion holds entirely because the developers bypassed standard software constraints to exploit the physical layout of the processor's internal pipelines.
It is a phenomenal manipulation of hardware architecture. But rescuing precision from catastrophic cancellation only stabilizes the physics matrix. The developer notes make it clear that the greater threat to the simulation comes from moments when the dynamic chaos of the ruined city generates data that is mathematically impossible to resolve.
Right. We are talking about the chaotic variables of a massive firefight, generating a scenario where the engine is asked to divide a dynamic coordinate by zero.
Or calculate the square root of a negative velocity vector.
When standard classical computing encounters an impossible paradox like that, it generates a very specific, highly destructive anomaly known as NaN, N-A-N, not a number.
A mathematical void. When the physical logic gates cannot resolve an operation, the silicon flags the output as undefined. It constructs a NaN.
To visualize how a NaN threatens the simulation, we have to frame it as a physical element within the ruined city.
Imagine a piece of highly contaminated, corrupted salvage dropped into the snowy streets after a skirmish.
An agent surviving the contaminated zone approaches this dropped loot. It occupies physical space in the rendering matrix. It is textured to look like a standard tactile backpack or maybe a weapon attachment.
But when the agent's wrist-mounted survival tech attempts to scan the item's properties, the resulting data is pure static. The item physically exists in the memory array, but its properties completely defy the established mathematical laws of reality.
Framing it as a localized anomaly or a biohazard to the system's logic is highly accurate. The IEEE 754 hardware standard forces CPUs to handle this contaminated data using a mind-bending paradoxical rule regarding equality.
The standard physically hardwires the hardware to evaluate a NaN as unequal to absolutely everything in the known universe.
Most crucially, the notes emphasize that a NaN is not even equal to itself.
That's the part that breaks people's brains.
If the simulation places two identical contaminated salvage crates side by side in the snow and asks the CPU if crate A equals crate B, the hardware logic gates will physically return a false state.
From an architectural standpoint, the hardware enforces this because of the philosophical nature of the void. If you generate two distinct, undefined mathematical states, you cannot logically prove they represent the exact same undefined value.
The physical architecture of the ALU is rigidly designed to reject any concept of equality the millisecond it touches a NaN bit pattern.
But the presence of this contaminated crate sitting in the snow doesn't instantly crash the game. The rendering engine can draw a corrupted object without failing.
The actual apocalypse triggers when the underlying game systems attempt to process and categorize that contaminated logic. The developer notes point directly to the simulation's automated inventory and sorting matrix as the critical point of failure.
In a simulation handling vast amounts of dynamic loot, the inventory system relies on strict sorting algorithms to organize freshly scavenged gear by armor ratings, weapon damage, durability.
The code backing the system is written in Rust, utilizing a function called SortBy. We can conceptualize this algorithm as a strict tournament manager overseeing an automated backpack.
This tournament manager runs a massive, rapid-fire single elimination bracket for the agent's gear. It pulls two items from the memory array, places them on the table, and demands a definitive comparative outcome.
It asks the raw math. Is the armor rating of item A greater than item B? Is it less than item B? Or are the two items exactly equal?
The tournament manager absolutely demands one of those three Boolean states to advance an item up the bracket and maintain the sorted structure of the backpack.
Here's where it gets really interesting. The collision of logic occurs the moment the tournament manager grabs the contaminated NaN crate. It places a pristine piece of scavenged tactical gear on one side and the NaN crate on the other and runs a comparative operation.
Because the hardware is hardwired to evaluate NaN as not greater than anything, not less than anything, and paradoxically not even equal to itself, the underlying silicon math fails to generate a valid Boolean state.
It throws its hands up. In Rust's architecture, this results in a none state. The math simply shrugs.
And a strict sorting algorithm like SortBy cannot process a shrug. The architectural rigidity of the system is compounded by the developers utilizing a specific Rust function called unwrap.
Right. In the context of memory safety, calling unwrap acts as an unbreakable legal contract. The developer is explicitly promising the software compiler that the incoming data stream is completely clean.
They are guaranteeing that the tournament manager will absolutely receive a definitive greater than, less than, or equal state for every single comparison.
So the moment the math hits the NaN anomaly and returns that none state, the legal promise is shattered. The unwrap contract is broken. And the reaction of the Rust compiler to a broken unwrap promise is incredibly violent.
The software doesn't log an error and politely skip the contaminated item, leaving it unsorted at the bottom of the backpack.
It refuses to skip the item because doing so would introduce undefined behavior into a highly volatile memory environment. If the sorting algorithm guesses where to place the corrupted item or ignores its boundaries, it risks overwriting adjacent memory arrays.
In a high-performance physics engine, overwriting adjacent memory is catastrophic.
The agent's spatial coordinates could be overwritten by the weapon damage values of the corrupted crate. Suddenly, the entire physics geometry breaks. Agents start falling endlessly through the solid concrete of the strait.
Abandoned cars launch violently into the sky because their gravity vectors were overwritten by corrupted UI data.
To protect the integrity of the system and prevent that kind of cascading memory corruption, the software architecture is designed to pull the emergency train brake. It triggers a system panic.
It intentionally and instantaneously terminates its own execution. The entire photorealistic snowy city freezes, the audio buffer hard stops, and the application spectacularly crashes to the desktop.
The simulation sacrifices itself to prevent data corruption.
And stopping this self-imposed apocalypse requires abandoning high-level software entirely. You cannot write a polite Rust script that says, please ignore the mathematical shrug.
By the time the software registers the none state, the unwrap contract is already broken, and the panic sequence is inevitable.
The developers must descend below the software layer, directly into the physical CPU registers, to perform what is essentially a microscopic digital heist.
To execute this heist, we have to examine the specific hardware scanner the tournament manager uses to compare floating point numbers. The assembly instruction is UCOMISS, unordered, compare scalar single precision.
This instruction operates deep within the CPU registers, specifically XMM0 and XMM1, which serve as a physical gladiator arena where the data values are pitted against each other.
We can equate the UCOMISS hardware scanner to the glowing orange diagnostic ring on our tactical agent's wrist-mounted survival watch. The scanner is a raw physical tool. It possesses no high-level logic.
It never turns off, and it must faithfully scan absolutely whatever data is shoved into the arena. When it scans pristine gear, it returns a clean comparative result. But when the software forces the scanner to read the highly contaminated NAND crate, the raw silicon of the CPU becomes confused.
The hardware logic gates attempt the comparative math, recognize the paradoxical impossibility of the NaN, and silently trigger internal microscopic hardware hazard lights.
The crucial detail here is the word silently. The UCOMISS scanner doesn't crash the simulation. The hardware itself is incredibly resilient. It simply logs the catastrophic anomaly by flipping physical electrical switches deep inside the processor's architecture.
Those silent hazard lights are located on a specific control register known as EFLAGS. We can visualize EFLAGS as a massive 64-bit electronic scoreboard hidden within the absolute center of the processor.
This scoreboard exists in a highly restricted privilege level called Ring 0, which is the locked kernel level of the operating system architecture.
The game software, the physics engine, the rendering of the snowy city, all of that operates in Ring 3, the user space level. The Ring 3 software is flying completely blind.
The hardware scoreboard down in Ring 0 is flashing red hazard lights, screaming that a NaN biohazard has entered the UCOMISS arena, but the game simulation is locked out. It cannot see the lights.
It just blindly proceeds, hits the broken unwrap promise, and panics.
To intercept the crash, the developers must bridge the gap between Ring 3 and Ring 0. They must observe those locked hazard lights before the software attempts to resolve the comparison.
The digital heist involves injecting a highly aggressive, low-level assembly instruction directly into the execution pipeline, the pushFQ instruction.
The pushFQ instruction is the physical breach. When the CPU executes this command, it is forced to take an instantaneous, comprehensive snapshot of that locked 64-bit EFLAGS scoreboard. It copies the entire sequence of hazard lights.
Once the snapshot is captured, the pushFQ instruction physically stabs that 64-bit data packet directly onto the top of the system's memory stack.
We can conceptualize this like an agent slamming a raw, contaminated data drive onto a metal spike at a tactical safehouse field desk. The data is forcefully pushed out of the restricted Ring 0 environment and lodged into an accessible memory space.
Immediately following the breach, the developers execute the getaway. The pop assembly instruction reaches onto the memory stack, grabs that raw 64-bit snapshot, and pulls it directly into the variables of the normal Ring 3 game software. The heist is complete.
The agent in our simulation has effectively recognized that their wristwatch UI is fundamentally broken and about to cause a fatal error. Instead of relying on the UI, they physically jam a specialized diagnostic cable into the locked port of the watch, bypassing the software entirely, and directly download the raw, screaming silicon logs straight from the hardware.
But the heist introduces a massive secondary challenge. The developers successfully extracted the data, but what they pulled into the game engine is just a massive string of 64 identical blinking electrical lights. It is raw, unformatted binary code.
To stop the crash, they have to decrypt the scoreboard and find the specific biohazard alarm buried in all that electrical noise.
Out of the entire 64-bit sequence, the developers only need to isolate 3 highly specific flags. The first is the 0 flag, or ZF, located at bit position 6 on the scoreboard.
When the UCOMISS scanner determines that 2 items are perfectly equal, the hardware flips bit 6 to a 1.
The second light is the carry flag, or CF, located all the way down at bit position 0. The hardware flips bit 0 to a 1 when the first item in the arena is mathematically smaller than the second item.
What's fascinating here is the third light the developers must monitor, the Parity flag, or PFF, located at bit position 2.
In classical computing architecture, the parity flag is traditionally a low-level safety mechanism used for detecting transmission errors. If data is traveling across the motherboard traces and electromagnetic interference accidentally flips a 0 to a 1, the parity flag counts the active bits to ensure the data wasn't corrupted in transit.
But the developer notes explicitly state that when the CPU is running a UCOMISS scan, it completely abandons that traditional rule.
It throws the traditional transmission rule out the window entirely.
The hardware engineers at Intel and AMD explicitly repurposed the parity flag specifically for floating point comparisons. When a UCOMISS instruction is active, the parity flag at bit 2 acts as a localized screaming biohazard warning light. If PF lights up, it means the hardware has explicitly detected a NaN anomaly in the arena.
So the targets are clear. ZF at position 6, PF at position 2, CF at position 0. But how does the Ring 3 software physically isolate those 3 specific lights out of a blinding string of 64 blinking binary values?
The notes outline the use of bitwise mathematical operations, specifically shifting and masking. Let's visualize the mechanics of this. Imagine a long physical sliding tray sitting on a field disk at a dark safe house in our ruined city.
Mounted on the sliding tray are 64 individual, blindingly bright light bulbs.
The 64 bulbs represent the raw EFLAGS snapshot, creating a massive amount of visual noise. The decryption algorithm needs to read the status of the 0 flag at bulb position 6, but the algorithm sensor can only read the very front edge of the table, which is position 0.
To bring the 6th bulb to the sensor, the algorithm physically grabs the entire sliding tray and forces it exactly 6 spaces to the right. As the tray slides, the first 6 bulbs on the right side get pushed completely off the edge of the table and fall into the trash.
They are permanently deleted from the snapshot. Now, our target bulb, the 0 flag, has been shifted down and is sitting perfectly at the front edge of the table.
That physical sliding action represents the bitwise right shift operation in the Rust code, executed as EFLAGS shifted right by 6. However, even with the target bulb at the front edge, there are still 57 other bulbs glaring brightly behind it on the tray.
The visual noise is still too intense for a clean read. The system must isolate the target bulb using a mask.
The masking operation is like taking a thick piece of dark cardboard, cutting exactly one single hole in it, and placing it completely over the sliding tray. The thick cardboard completely blocks out the electrical noise of the 57 other bulbs.
The sensor is left staring at a clean, perfectly isolated 1 or 0 shining through the single hole.
The cardboard mask is the bitwise AND operation, coded as AND1. It structurally zeroes out every single bit in the sequence except for the target bit, perfectly isolating the necessary Boolean state.
The software executes this sliding tray and cardboard mask maneuver 3 distinct times in rapid succession. It shifts and masks for the 0 flag, the carry flag, and the parity flag.
When the decryption completes, the software analyzes the 3 isolated values. If it discovers that ZF, CF, and PF are all lit up simultaneously, if the extracted sequence yields a 111 state.
The 1-1 state.
The 111 state is the undeniable, hard-coded, raw silicon signal of an unordered calculation. It confirms absolute mathematical contamination.
The developer successfully breached ring 0, copied the scoreboard, decrypted the hazard lights, and confirmed the presence of the biohazard crate in the sorting arena.
Crucially, they achieved all of this in a fraction of a microsecond, intercepting the logic flow before the strict tournament manager attempts to process a shrug, thereby preventing the unwrapped broken promise and saving the snowy city from crashing.
The engineering required to pull that off is staggering. But it begs a massive architectural question. Why go through the immense computational effort of ring 0 heists, sliding trays, and bitwise masking?
The developer notes reference a standard software function called F32 From Bits. If the floating point decimal logic is the root cause of the mathematical panic when it encounters a NaN, why not bypass the floating point unit entirely?
Right, why not simply strip away the decimal rules, treat the 32 bits as a pure integer, and sort them that way?
Integers are just raw whole numbers. Integers do not possess a concept of NaN. They never return a mathematical shrug. Why not just convert the data and bypass the entire crisis?
It is an incredibly tempting shortcut, and the logic seems sound at a high level. But the developer notes dedicate significant space to unpacking exactly why that shortcut is a fatal, catastrophic trap. It represents a fundamental misunderstanding of how physical memory and typecasting function in modern computing.
Let's bring the contaminated salvage crate back into the safe house.
Using the S32 From Bits function performs what computer scientists call a typecast. A typecast does not manipulate the physical underlying binary data residing in the RAM. It does not magically rearrange the microscopic electrical charges of the 1s and 0s to sanitize the corruption.
A typecast is purely semantic. It is exactly like an agent taking a high-tech label maker, printing a bright, white, pristine sticker that reads clean integer medical supplies, and slapping it directly over the glowing green biohazard logo on the side of the corrupted crate.
That is the perfect architectural equivalent. You have successfully instructed the high-level inventory software to view the crate as clean integer data. But the lethal mathematical radiation, the underlying bit pattern of the NaN, is still pulsing away inside the container.
The electrical contents haven't been altered by a single electron, and the hardware layer doesn't care about software stickers.
The hardware is incapable of being fooled by semantic labels. The moment the engine's sorting logic attempts to actually perform a comparative operation, the moment it demands to see what's inside the crate to weigh it against another item, the CPU looks entirely past the superficial software label.
It reads the true, raw binary values. It rips the sticker right off.
And when it rips the sticker off, the CPU instantly recognizes the specific bit pattern of a floating point anomaly. It forcefully routes the data out of the integer pipeline and right back into the floating point unit.
The FPU calls the exact same UCOMISS Gladiator instruction. The scanner reads the raw biohazard, the internal hazard lights trigger, the math returns a shrug, the unwrapped promise breaks, and the exact same system panic triggers, freezing the snowy city and crashing to the desktop.
Slapping the integer label on the crate achieved absolutely nothing beyond wasting processing cycles. It only delayed the inevitable total system crash by a single microsecond. It is a false cure.
And the developer notes deepen the terror of this false cure by analyzing the 2 distinct variants of NaN biohazards defined by the IEEE 754 standard, revealing how they interact with memory arrays in terrifying ways.
The standard defines SNaN and QNaN. Let's break down the mechanics of the SNaN first, the signaling NaN.
A signaling NaN functions as an active, highly volatile hardware grenade. It is designed by hardware engineers to be as loud and destructive as possible.
The literal millisecond a mathematical operation touches the bit pattern of an SNaN, the CPU itself throws an invalid operation exception. It violently halts the execution thread at the physical hardware level immediately.
Slapping a safe integer label on an SNaN doesn't stop the pin from being pulled. The moment the sorting algorithm attempts to move the crate, the grenade detonates, and the application dies instantly.
And the second variant, the QNaN.
QNaN stands for Quiet NaN. In the context of a massive simulation processing billions of physical interactions, a quiet NaN behaves like a highly contagious silent virus. It is infinitely more dangerous than the grenade.
A virus that doesn't trigger an alarm.
It explicitly suppresses hardware exceptions. When an operation touches a QNN, it doesn't halt the thread. Instead, it quietly infects any calculation it touches, transforming the output into another QNN.
Imagine the engine calculating the trajectory of one microscopic piece of flying concrete debris. If the memory sector holding that coordinate gets flipped by a random cosmic ray or an overflow error, it becomes a QNN.
So we have a single microscopic infected shard of concrete flying through the air.
That shard mathematically collides with a snow-covered car. Because the fundamental rule of floating point math dictates that anything multiplied or added to a NaN instantly becomes a NaN, the car's entire spatial physics array is instantly corrupted.
The car's velocity vectors turn into static. The simulation suddenly calculates the car sliding wildly into a concrete barrier, instantly corrupting the barrier's structural integrity values.
The barrier shatters, sending hundreds of corrupted, infectious chunks of geometry into a group of agents attempting to take cover.
Suddenly, the spatial coordinates, the health pools, and the weapon states of every agent in the sector become corrupted data. And because the QNN is silent, the system hasn't thrown a panic yet.
Strict tournament manager hasn't even looked at the data to trigger the unwrap failure.
The silent virus propagates exponentially through the physics matrix. One infected snowflake touches another. Before the engine's error-checking protocols even realize what is happening, the entire memory architecture of the physics engine is completely overwhelmed by corrupted, undefined data.
Eventually, the rendering engine attempts to draw the snowy city based on those undefined coordinates, realizes the geometry is mathematically impossible, and triggers a spectacular, unrecoverable crash.
If typecasting is a fatal trap and QNNs can silently consume the entire matrix, how do the developers actually engineer a permanent solution? How do they safely sort the automated backpack and keep the city rendering when a biohazard crate inevitably drops?
The notes reveal the ultimate architectural fix, a masterful implementation of memory sorting called total clamp, which stands for total ordering.
Total ordering succeeds where the false cure of typecasting failed. How does it manage the hardware?
Total ordering completely abandons traditional floating point mathematical comparisons, but it does so structurally, not semantically. Instead of acting like an inventory manager looking at superficial price tags and panicking when it sees a NaN label, Total Clamp equips the system with a deep, penetrating SHD tech pulse scan.
A pulse scan that looks past the flute.
This pulse scan completely ignores the floating point context of the data. It doesn't care if the container is meant to represent an armor rating, a physical coordinate, or a biohazard. The algorithm penetrates the container and looks strictly, exclusively at the raw binary molecules, the exact sequential pattern of ones and zeros, and evaluates them purely as unsigned integers.
But wait, didn't we just establish that treating them as integers was the fatal trap?
We established that labeling them as integers and feeding them back to the floating point unit was the trap. Total ordering never sends the data to the FPU. It never triggers the UCOMISS scanner. It performs the comparative logic entirely within the integer arithmetic logic unit, comparing the raw bitwise magnitude of the patterns.
And because it stays in the integer ALU, it restores mathematical order to the chaos. In the realm of raw binary integers, the concept of undefined simply does not exist.
There is no possibility of a mathematical shrug. Every single conceivable 32-bit pattern of ones and zeros has a strict, definitive, sequential integer value. A binary pattern containing mostly ones is definitively larger than a pattern of mostly zeros.
Exactly. So let's look at how the IEEE 7504 standard physically constructs a NaN. To flag a container as a NaN, the architecture requires the entire 8-bit exponent segment to be switched onto 1, along with specific bits in the Mantissa.
So when the total clamp pulse scan sweeps over the NaN biohazard crate, it doesn't see a mathematical void. It just sees an incredibly dense, massive cluster of binary ones.
Yes. And because the integer ALU evaluates that dense cluster of ones strictly as a raw number, it mathematically views the NaN biohazard as possessing an incredibly massive integer value.
In fact, because of the exponent structure, the integer ALU evaluates the NaN as a number structurally larger than the binary representation of absolute infinity.
That completely flips the paradigm. The strict tournament manager doesn't panic, it doesn't hit an unstate, it smoothly grabs the biohazard crate, recognizes its massive binary integer value, and quarantines it safely at the absolute back of the warehouse.
It isolates the corrupted data at the extreme end of the sorted array, completely out of the way of the pristine scavenged gear. The software never breaks the unwrapped promise, the hardware hazard lights remain dark, and the snowy city simulation continues rendering without dropping a single frame.
It is an incredibly elegant structural solution. But the developer notes also reveal that total ordering fixes another bizarre architectural edge case regarding the concept of zero.
In standard high-level algebra, -0 and +0 are conceptually identical. They equal each other perfectly. But deep within the physical memory of the computer, their binary molecules look structurally different.
Because of the IE 754 standard, -0 has its leading sign bit physically flipped to a 1, +0 has a 0.
If the integer ALU pulse scan simply looked at those raw patterns, it would see a massive difference. Because -0 has a leading 1, the integer ALU would evaluate it as an incredibly large number, sorting it completely wrong.
To correct this, the total comp algorithm utilizes specialized 2's complement transformations. Before the integer comparison occurs, the algorithm applies a mathematical bit flip to the negative values.
By strategically inverting the bits using an XOR mask, the architecture mathematically aligns the structures. It ensures that structurally different numbers that conceptually equal each other are sorted perfectly adjacent to one another.
It flawlessly sorts negative floats, positive floats, and quarantines NaNs, creating a fail-proof sorting architecture.
The total ordering architecture secures the inventory matrix. We've conquered subtraction precision with fused multiply add. We've conquered sorting panics with total ordering. But the developer notes outline one final, incredibly aggressive technique required to keep the simulation alive.
There is one mathematical operation that is practically a death sentence for a physics engine attempting to calculate dynamic movement.
Division. Specifically, the architectural nightmare of dividing a coordinate by 0.
This section is titled Singularity Avoidance and MXCSR Hijacking. When the chaotics of the firefight accidentally asks the silicon to divide an incoming velocity vector by pure 0, what physically happens inside the processor?
It creates a literal mathematical singularity, a computational black hole. If the physical logic gates inside the math unit attempt to resolve an electrical voltage divided by 0 voltage, the gates enter an unresolvable loop.
They lock up, spinning in an infinite paradox trying to calculate infinity.
To prevent the physical chip from literally freezing forever, the CPU hardware is designed to immediately throw a massive system-halting exception. It screams for the operating system kernel to intervene and kill the offending program.
The OS boss steps in and terminates the simulation. To survive the black hole, the developers implement what they call an epsilon barrier.
Epsilon is a mathematical term representing an incredibly small quantity, a microscopic decimal sliver, sitting just barely above true 0. In the code, before the engine ever sends a division command to the hardware, it rigorously inspects the denominator.
If that value drops dangerously close to pure 0, close to the event horizon of the black hole, the software physically overwrites the data in the register.
It establishes a physical floor beneath the calculation.
It forces the tiny epsilon value into the container instead of 0. The hardware executes the division smoothly, gliding safely right over the mathematical void, never actually touching the 0 state that would trigger the exception.
But the notes reveal the developers go even further. If a calculation is deeply embedded in a parallel processing thread, where checking every single denominator would cripple performance, and a crash is absolutely inevitable, they execute the ultimate microscopic heist.
They bypass the OS boss entirely by hijacking the MXCSR control register. What exactly is this register?
If the floating point processor is a massive automated math factory, the MXCSR register is the absolute master control panel governing the factory floor. It contains a highly specific set of 32 bits that dictate exactly how the hardware architecture reacts to catastrophic mathematical events. Normally, the operating system kernel locks down these settings.
The OS boss configures the panel to say, If the factory hits a divide by zero black hole, immediately sound the sirens, halt the assembly line, and crash the program.
But the game developers write extremely low-level assembly code to hijack this control panel. They execute instructions like STMXCSR to save the current state of the panel, and then they physically manipulate specific bits known as exception masks.
They max the hardware exceptions.
Specifically, they target bit 9 on the MXCSR register, which is the zero divide exception mask. By forcefully flipping bit 9 to a 1, they are literally commanding the physical silicon of the CPU to swallow its own mathematical errors. They place noise-canceling headphones over the ears of the operating system.
When the black hole hits the factory floor, the hardware generates the paradox. But because bit 9 is flipped, the sirens never sound. The math factory swallows the error, outputs a safe default NaN or infinity state, and keeps the engine running without ever alerting the operating system boss that an impossible event just occurred.
The thread executes the risky calculations, survives the black holes, and then the developers carefully restore the MXCSR control panel to its original safe state using LDMXCSR before the operating system even realizes the hijack occurred. It is a breathtaking display of low-level software engineering dominating hardware architecture.
So, what does this all mean? Let's synthesize this incredible journey into the metal. We started by looking at a snowy, ruined city simulation. Agents flawlessly snapping to cover, volumetric snow accumulating on tactical gear, millions of concrete debris particles calculating perfectly in real time, and we tore all of that comfortable illusion away.
We descended far beneath the high-level game engines, past the Rust compilers straight down to the atomic logic gates of the CPU. We analyzed the physical limitations of a 23-bit Mantissa container, watching how shifting decimal points pushed tiny fractional details into the void, causing catastrophic cancellation.
And we saw how engineers exploit the massive internal fused multiply-add hardware pipelines to weaponize negative math and extract that lost silica noise, saving the cover physics.
We tracked the invisible biohazards, the NANs, and analyzed the paradoxical hardware rule that forces them to be unequal to themselves. We saw how these contaminated mathematical voids shatter the strict unwrapped promises of the tournament manager, threatening to plunge the entire inventory system into a cascading memory panic that would rip the simulation apart.
We observed the execution of a ring zero digital heist, violently stabbing the 64-bit EFLAGS hardware scoreboard onto the memory stack. We used sliding trays and cardboard masks to isolate the repurposed Parity flag, extracting the exact 111 biohazard warning light.
We exposed the fatal, catastrophic trap of typecasting, proving that simply slapping a semantic integer label on a volatile SNaN grenade or a viral QNaN cannot fool the hardware. The CPU always rips the sticker off.
And finally, we saw the ultimate architectural fixes, the deep penetrating SHD tech pulse scan of total ordering, utilizing 2's complement bit flipping to safely quarantine biohazards mathematically beyond infinity. And we watched developers brazenly hijack the MXCSR master control panel, flipping exception masks to force the processor to swallow its own black holes and keep the snowy city alive.
It highlights a profound architectural reality. The developers had to adopt a completely silicon-agnostic approach. They couldn't just write good software. They had to fundamentally outsmart the hardware at an atomic level to maintain the simulation. It requires an absolute mastery of the metal.
It truly changes how you perceive the screen. But before we sign off, I know you have a final provocative thought for our listener to mull over, something that builds on everything we just discussed regarding memory architecture.
I do. It is a mind-bending extrapolation regarding the future of simulation. Everything we explored today, the strict unwrap panics, the total ordering pulse scans, the shifting of the EFLAGS scoreboard, relies entirely on the absolute foundation of classical computing.
Classical computing architecture.
The absolute uncompromising strictness of the binary state. A physical transistor is either a definitive or a definitive one. It's a strict yes or a strict no. That architectural rigidity is exactly why a single undefined NAND state causes a total system panic. The classical hardware demands absolute certainty, but look to the rapidly approaching horizon of hardware architecture. Look at quantum computing.
Quantum computing completely discards the traditional transistor for qubits.
Exactly. And the defining foundational characteristic of a quantum qubit is the principle of superposition. A qubit does not exist as a strict 0 or a strict 1. It exists in a fluid, probabilistically weighted state of being both a 0 and a 1 simultaneously.
The value is both true and false at the exact same physical moment.
So here's the question for you to explore on your own. If today's state-of-the-art classical hardware completely panics and crashes a massive, billion calculation simulation over one single undefined mathematical state, how will a future quantum strict tournament manager possibly run a sorting bracket for an agent's inventory?
How will a quantum sorting algorithm evaluate two pieces of gear when their statistical values exist in superposition, where item A is simultaneously greater than and less than item B at the exact same physical moment?
The entire logic of comparative sorting, the deep integer pulse scans, the rigid hardware scoreboards we just spent the hour dissecting, absolutely none of it will apply to that architecture.
It will all have to be completely reinvented from scratch. The physics engines of the quantum future will have to navigate a computational world where a mathematical paradox isn't an error state that requires a panic, but the foundational reality of the physical hardware itself.
That is an incredible paradigm-shifting thought to end on.
Thank you so much for joining us on this exhaustive deep dive all the way down to the raw metal. Keep exploring those unseen mathematical systems sustaining the world beneath your simulations, and we'll see you next time.